So we still have a little bit of wrap up to do with this lecture, so I will continue to talk a little bit on lecture 5 slides, and then we'll switch over to lecture 6 when it's time for that. Okay, so we have been talking quite extensively about this receiver, and I claim that this is a minimum distance receiver for PAM, and actually this was also proven by what we did last. So there is only a few minor wrap-up things here to make it extra clear, hopefully. So the idea with the minimum distance receiver is that we would like to compute distances squared for all L, for L equals 1, 2, 3, up to M. And it turns out that the final expression for this, for the distance squared, is this. And what we are aiming for in a minimum distance receiver, if you remember, is to find the signal index, m hat, as this, the arg min of the distances. So we have the distances here, and we compare them for L equals 1, 2, 3, 4, 5, up to capital M, and the index which has the minimum value is our m hat. Okay. So in this case, that will be the arg min over L of this expression. Okay. So we will compare this expression for different values of L and pick the one which is the smallest. So this term doesn't depend on L, so why even compute that? Because it will not factor into the decision. This term doesn't depend on L, so that we don't need to compute either. And EH is just a positive number which multiplies everything. Okay. So instead of computing the distance, let's compute the thing that matters, the difference between the different L's, the different distances. So this is just the arg min of y0 divided by EH minus AL, like this. So instead of computing the full distance, let's compute the part of the distance expression that matters, the one that differs for different L's. And this we can write in terms of the input to the slicer, the z variable. Okay, like this. The slicer outputs the actually not the index but the value that minimizes this. So it outputs then a hat 0 equal to a m hat, like this. It picks the index, which is the smallest. That's what we're looking for. But instead of outputting the index, it actually outputs the corresponding symbol. So to illustrate the functionality of the slicer, this box here, has a certain input and then a certain output. And the output is the value inside this set curly A, which is closest to the input. Okay. So if A is equal to, say, -3, -1, 1, and 3, where -3 is A1, -1 is A2, A3, and A4. So we have a symbol alphabet like this. Then if the input, if we plot that on this line, and the input to the slicer is zk, then we can mark on this line the signal points. So we have the origin here 0, so this is the number line, and then we have -1 and 1. Let's put 2 dots there. This corresponds to 2 of the amplitudes, and then we have -3 and 3. Okay, so these are the transmitted amplitudes. The received amplitude Z0, CK, will be the transmitted amplitude plus the noise contribution. Okay, so you will end up somewhere on this line, and the slicer outputs the purple point, the signal point, which is closest to the input. Okay, so one way to illustrate this is to draw boundaries between points, which is in the middle between the points. So the middle point between -3 and -1 is at -2, right? Okay. So then we know that if the input is to the left of this boundary, then what will be the decision? So for all points which are to the left here, what will be the decision? It will be that we guess that the amplitude was -3, because -3 is closer to all the points which is to the left of this boundary. Okay. Inside here, the decision is that A hat is -1, because all the points here on the number line inside this region is closer to -1 than to any other point. Okay, and then we have a boundary here also, when A hat is equal to 1, and then for all points to the right here, A hat is equal to 3. Okay. So the slicer has an input and an output, and the output is the value in this set which is closest to the input. And one way to illustrate that is to draw a line where we have here all the possible inputs and decide in which region different outputs belong to. So anything that ends up from here to here will be decoded as -1, that the amplitude -1 was transmitted. So this is known also as the decision region for alternative A. Okay, so this happens to be A2, right? In this case. Okay. So for each signal alternative, we have a decision region. And basically, the slicer only says, look at the input and say, to what decision region does this input belong to? And then spits out the corresponding signal alternative. Was this relatively clear? Okay. So by doing this, we have now a minimum distance receiver. So it was a pretty long derivation. But remember that we started by saying that in the noise-free case, the output is equal to the A hat k is equal to AK. And why is that? It's because the input, Z of k, happens to be AK. So the rest, what we did is only to motivate that this was also actually a minimum distance receiver, with all the math that came after that. Okay, so any questions before we continue? No? Okay, so then we have passband PAM and baseband PAM. So what is the meaning of these two words? This is what we've been talking about for the longest time now. This is a baseband PAM process. Baseband means basically means that H, if we take the Fourier transform of that, is centered around 0. This is sometimes called the baseband. And it has a certain bandwidth W. Now, if we want to use radio, we cannot use baseband. We have to modulate this up to a carrier frequency. It could be like a gigahertz or 100 megahertz or something like this, but at least it cannot be transmitted around basebands. We want to move this up to be centered around a certain carrier frequency. So the carrier frequency, if we pick a carrier frequency, that we like, and then we can move the spectrum of the transmitted signal, the baseband, to be centered around the carrier frequency, but simply taking the baseband signal and multiply with the carrier, where the carrier has the frequency we like. Okay. So if we have baseband, we can form the corresponding passband signal. Okay. Now, the trouble in doing this is that the bandwidth of the passband signal is twice the bandwidth of the baseband signal. So that's a little bit problematic because we would like to be efficient. We would like to use as little bandwidth as possible. Luckily for us, there is a way of transmitting two baseband processes using this bandwidth. Okay, and the trick is that this is a cosine carrier, and we can add on top of this something with a sine carrier. And if we do, that purple signal will also be contained in this spectrum, right? So if we had like a purple signal here also, that was a badly drawn. So if we have another baseband, you get a point. If we have something here, we can multiply that with the sine carrier, and that will also end up being occupying this bandwidth of 2W. Okay, so here we have transmitted something with a cosine carrier, something with a sine carrier. The beauty of this is that at the receiver we can separate these without any crosstalk. Okay, so we can. It seems like here that we lost in spectral efficiency because we doubled the bandwidth, but the beauty is that we can actually transmit two of these PAM signals in parallel, one on a sine carrier and one on a cosine carrier. And in more detail, it works something like this. So this is what's known as an in-phase quadrature phase modulator, where the input is still bits and the output is still a signal. The difference is that this signal is now at a certain carrier frequency, determined by FC. And what we have essentially is that these bits are then divided up, so half of the bits go over a cosine carrier and half of the bits go over a sine carrier. And at the receiver, we can actually separate these. So we have a question.
Yeah, why do you have a factor of square root of 2?
Okay, so this mystical square root of 2 here has no practical consequence. It only has this for symmetry in the math and so forth. So you can pick this as anything you like. The beauty of this is that the power of the signal here is equal to the power. Never mind. It's not important. Okay, but it's nice. Some equation becomes symmetrical, and the important thing is that we have a cosine here and a sine here at exactly the same carrier frequency. That's crucial. Okay. And then a matched filter or minimum distance receiver to this looks something like this. So we have the transmitted signal plus some noise. This is the received signal. And then we basically have something which is matched to the cosine carrier and something which is matched to the sine carrier. And then there is no crosstalk between these two things. Okay. So I realize that this goes very quickly now, but the reason why I want to show this is that we now get two-dimensional constellations instead. So here we have a constellation where we have signal points on one axis. But now if we have two systems which are working in parallel, we have one which goes along a sine carrier, and then we have something perpendicular that goes along a cosine carrier. And then we get these two-dimensional constellations. So the one to the left, so anyways, these are known as quadrature amplitude modulation, or QAM. And the constellations now, instead of being along the line, we have it in the plane like this. So here are our signal points, like this. And then we have decision regions now, which are not only, what should we call it? It's not only, for instance, you know, a PAM decision region would be between these points, right? But now instead of having along one line, we have a two-dimensional decision variable. So then we have these regions. So this region here are all the points in the plane which are closest to this signal point. Okay, so this is now the decision regions. These constellations is used quite heavily in practice. So Wi-Fi, for instance, have these type of constellations. It actually has a bunch of different constellations depending on the channel conditions. So if you know when you put up your laptop, you get different data rates depending on how close you are to the base station and how many are sharing the channel. But one thing that matters is how good your signal-to-noise ratio is. And then one can go from the simplest constellation, which are just 2 points like this, to a constellation that looks like this, where you have 64 QAM, where 64 signal alternatives. And as a matter of fact, I think I bought a new router during Christmas as a present to myself. And if I understand it correctly, in it has a non-standardized constellation where it has 10,024 points in, which is quite extreme. And the reason why you want to have many points here is that you get many bits per symbol, or another way to say that the spectral efficiency increases. So in a Wi-Fi channel 20 megahertz, you can get now different data rates depending on which constellation we use. Okay, so any questions? No. Okay, let's go and be a little bit random. To analyze how good we are, a physical layer, we would like to say something. What is the probability of making a wrong decision? So, sometimes this output is not equal to this input, and then we make an error, right? And we make an error because we have noise. We have picked our signals, the pulses, the transmit pulse and the receiver impulse response, so we have fulfilled the Nyquist criterion, so we don't have any inter-symbol interference. So the only thing that can hurt us is the noise. And of course, we would like to ensure or pick a constellation we would like to answer the following question. What is the error probability for these constellations? So we would like to compute this. And to do that, we need to model the noise somehow. And the noise is something that is unpredictable to us. So the standard way to model the noise is to say that it's a random process, something which is unpredictable to us. We also need to say something about what is the probability that we transmit one of these points. Because we are transmitting different points, right? We have different data, for instance. What can we say about these bits, for instance? And then the standard assumption is to say, okay, these bits are unknown random variables. Unknown and random for the receiver, but not for the transmitter, of course. The transmitter knows these bits as they arrive. The transmitter has full knowledge about this. But from the perspective of the receiver, the bits are random. Okay, we don't know what the transmitter transmitted, so let's model them as random variables. Okay. So if you remember from your courses in basic probability and so forth, there are distribution functions, then there are density functions, there are probability mass functions, expected values, and so forth. So I assume that you've seen this material before. If you have not, there is a little bit of review material on Canvas for this. But I will just go through this rather quickly now to set some notation. Okay. So the cumulative distribution function CDF and the probability mass function of a discrete random variable are defined like this. Okay. So x here takes on certain numbers. So think of x maybe being a bit, could be 1 or 0. And then there is a probability that x is equal to 1, say, and a probability that x is equal to 0. This is called the probability mass function. And if we want to compute that the probability that x is less than some value, then this is called the cumulative distribution function. For continuous random variables, we have essentially the same thing, that we have this CDF. However, we don't have since this is now a continuous function, we can take the derivative of it, and then we get what's known as the probability density function. So if it's we have mass functions when we have discrete random variables, we have densities when we have continuous one. And then we can compute probabilities using these CDFs or PDFs and PMFs according to this. Okay, so if I'm interested in knowing the probability that x is between two limits here, we can compute that from the CDFs by taking the CDF of the upper limit and subtract off the CDF of the lower limit, or we can integrate the PDF over these limits. Okay, so there are two ways of doing the same thing. Which one we choose is which one is the most convenient. Same thing for discrete random variables, except now we have, instead of an integral here, we have a sum. So I hope this is not news to you. If it is, then you need to recover this material rather quickly, I would say. Okay, expectations. Expectations is like averages. Okay, so if we have a random variable, the expectation of this is E. E is not energy or anything like this. Now this is an operator. It says E of x here means what is the expected value of x. And that is defined as this integral. So we have the CDF of it, and we multiply with u, the integration variable. We integrate this, we get a number, and this we call this the expected value. The expected value for a function of a random variable. Okay, so if we have a random variable, if we take a function of that random variable, we get a new random variable. Right. So a function of a random variable is a random variable. And then the expected value of a function of a random variable is simply computed like this. Okay, so the only thing which differs is that the g here pops up here. Okay, we used the same CDF as we did, a PDF as we did up here. Okay. So that's the only difference. then we can put in different functions here. So maybe we take the square. So g is the squaring function. Then we have e to the x squared. And then, therefore, we put in u squared before the PDF when we integrate. So this is known as the second moment. The variance is the expected value of x, where we subtract of its expected value squared. Okay. So it's very complicated to say, but this is a measure on how far the random variable deviates from its mean on the average. Okay, so, and the square root of this is the standard deviation. And we have linearity in this expected value. So the expected value of a times x plus b is a times e of x plus b. And this follows very quickly from the definition of expectation of this function. Right? Because we have integrals here, we can put out the a, and the b just also goes out, and then we get this result. Are these things familiar to you? Okay. Okay. Good. So then we have the next concept is statistical independence. So we say that two random variables, x and y, are statistically independent if their joint CDF, which is defined like this, factorizes into the CDFs of each of the random variables. Okay, another way to say that is that if we have the joint PDF, then it factorizes as the product of two marginal PDFs here. And then we can form the expected value of x times y, and look something like this. Then it turns out to be the product of the expected values. So these are things from independence. Again, these are not terribly difficult to prove. If you're interested in knowing why this is the case. Okay, now we've gone through some basic random stuff. So let's put this to use and look at the transmitted bits. So remember the bit, the ith bit that we would like to transmit. So I here is some time index. So we will model this as a discrete random variable. RV for random variable, not recurring. Yeah. Then there is a probability mass function for this. So f here now for probability mass function, and then the random variable as an index bi, and then it takes on a value u. Okay. Brackets here just to indicate that it's a discrete variable. So this is by definition the probability that bi is equal to u, which in the case of bits is very simple. It has two values, 0 or 1, and there is a probability associated with this. So we can think of this as being equal to some number pi when u is equal to 0. And then we need to specify what happens when u is equal to 1. So if the probability that bi is equal to 0 is pi, what is the probability for bi being equal to 1? Exactly. So 1 minus pi here. So essentially, the statistical behavior of a bit is determined by the probability that it takes on one of its values. Okay. So for instance, the probability of it being 0. Actually, I want to do this the other way around. 1, 0. This. It doesn't matter, but yeah. Okay, so we will then typically assume that bits are independent of each other. So for different time intervals, these are independent random variables. And also we would assume that they are individual bits are equally likely to be 1 and 0, meaning that pi is 1/2. Okay. So the key thing that shows up on exams and so forth is like we assume that the bits are equally likely independent. Okay. And this is the same thing to say that the probability that bi is equal to u is equal to 1/2 when u is equal to 0, and therefore u is equal to 1, and therefore 1/2 when u is equal to 0. Okay, so that's equally likely, and the probability that, say, b0 is equal to u0 and b1 is equal to u1 and b2 is equal to u2, etc. and say bk minus 1 is equal to uk minus 1. That is equal to the product. Actually, let's go from 0 to n. It's the product of the probabilities like this. Okay, so this is equally likely and this is independent. And if both things happens at the same time, all of these probabilities are equal to 1/2, regardless of what u is. And then we have 1/2 raised to the power of n, or 1 divided by 2 to the power of n. Like this. So basically what this says is that if we take n bits and would like to compute the probability for that these bits is a particular pattern, u0, u1, u2, and so forth, then the probability for doesn't matter. All patterns are equally likely, and their probability is 1 divided by the number of patterns. Okay, 2 to the power of n is the number of bit patterns. So, for example, if we have 2 bits, b0 and b1, could be 0, 0, 0, 1, 1, 0, and 1, 1. And say that these are mapped to the amplitudes A1, A2, A3, and A4. The probability that B0, then the probability that A is equal to some value here, say A1, okay, small a equals A1. So what is the probability that small a is equal to A1? Well, it's the probability that B0 and B1 takes on the pattern 0, 0. Okay. So this is equal to the probability that B0 is equal to 0 and B1 is also equal to 0. And what is this probability then if we have equally likely independent bits? Yes, 1 over 4. We have 4 alternatives. All of them are equally likely. They have to add up to 1, so 1/4. Okay. And this is true for all signal alternatives. Okay. So if we have independent equally likely bits, then all signal alternatives in a PAM constellation, or a QAM constellation for that matter, are equally likely. Okay. Let's look at the transmitted pulse. So the transmitted pulse is A times HT, right? If we just look at the first symbol that we transmit. So we have some bits, and depending on their, what the bits are, we get an amplitude. But since the bits are random, and the amplitude is a function of the bits, the amplitude is also random. Okay, so small a is a random variable. And we know what the probability for small a take on different values are. Okay, so the transmitted pulse A times HT has energy. What is the energy? Well, it's an integral of the signal magnitude squared, and then integrate it for all times. Okay. We can write this as the amplitude squared times the integral from minus infinity to infinity of the magnitude squared of the pulse, like this. The last integral here, or the integral, what is this? Equal to. What is this called? Yeah, see people saying energy without making the noise, right? So this is the energy. I asked this same question of 3-4 times today, right? So this is the energy of the pulse, EH, okay? This thing here is a random quantity, right? A is random, and then the magnitude square of it is also random. So this is random. Okay. So what we can say about the energy of the symbol is it depends, right? It could be different energies, and it has different because. Why can it have different energies? It's because it has different amplitudes. And why can it have different amplitudes? Well, it can carry different bits. Okay? So depending on the bit pattern, the energy of the transmitted pulse multiplied with that amplitude will be different, of course. Okay? But we would like to say something about the average energy. Okay? So the average or in other words, expected energy per symbol is then the expected value of the magnitude squared of A times EH. Okay. Now, there is a little bit of so this E here has nothing to do with energy. It's the expected value operator. This is the energy of the pulse H. Okay? And to make everything worse here, we will call this the energy per symbol, ES. Okay, so there are 3 E's here. The energy per symbol, which is the expected energy per symbol. We have the expectation operator here. And we have the energy per pulse. And let's call this the energy, the constellation energy. And let's call that EA. So this is EA times EH. Okay. So let's now compute EH for our example. So we have our bits here, we have our different amplitudes. We know what the probability that small a takes on one of these amplitudes, and we figured out that that is 1/4 for each of the possibilities here. Sorry for the noise. In general, it is let me write this out. So EA is the expected value of the amplitude squared. And so this is a sum from small m equals 1 to big M, and then the value of the probability that small a is equal to AM multiplied with AM squared, like this. Okay, so we know that small a can take on, small a can be A1, A2, A3, or A4. So the probability of this happening, we multiply that with the magnitude squared of the amplitude, and then we get the expected value of the amplitude squared. Okay, and this happens to be then, this is equal to 1 over M for independent equally likely bits. So basically it's 1 over M and then the sum from 1 to M of the amplitudes squared, like this. So for our example, when we have 4 signal alternatives here, well, let's make an example. So if curly A is -3, -1, 1, 3, which is then equal to, that's A1, A2, A3, and A4, then EA is 1/4, okay? And then we take the amplitude squared. So it's 9 plus 1 plus 1 plus 9. This is 20 divided by 4, or equal to 5. Okay, so for independent equally likely bits, we can calculate the constellation energy, but by simply taking the constellation points, square them and add them together, and then divide with the number of points. So it's not so difficult, right? So it would be different if the different amplitudes have different probabilities, but that will seldom be the case in this class. Okay. Let's take 15 minutes now.